Hi everyone. So next, I would like to discuss how to estimate the parameter beta. So last time that we discussed how to estimate beta naught, beta 1, beta hat by the R language, but this time I would like to give a theory. And to give a theory to estimate beta hat, I would like to introduce the matrix representation because with this, it becomes much easier. So let y be a vector of y1 to yn. So this is the response variable for all n observations. So in the previous example, these are percentage of undercount for 159 counties, n is 159. And x is a matrix for predictors. So each column corresponds to one variable, but the first column is corresponding to intercept. So you can see that the y1 is equal to beta naught times 1 plus beta 1 times x1 up to beta p times xp1 plus epsilon 1. So with this notation, the linear model for n observations becomes this simple form. So this is even much simpler than general notation for all observations. Y is equal to beta naught plus beta 1 x1 plus up to beta p xp plus epsilon. So now that we need a principle on how to determine beta. So for simplicity, we consider a single linear regression. Maybe simple linear regression is more common word. And okay, so we replace beta naught by A, beta 1 by B. How to determine? What's the principle to determine A and B? Then principle is here. So the least square estimator of AB, denoted by A hat, B hat, is the pair of numbers which minimizes sum of squared vertical distances in the scatter plot of XY. So here, the X and Y, and we have observations, 1, 2, 3, 4, 5. And we determine the best line, y is equal to a plus bx, as the line, this blue line, which minimize the distance between, the square of the distance between each point and the line. So intuitively, we can imagine that such line is determined uniquely. You can see that if this line is above this place, more observations have larger errors, especially these have larger errors, so sum of squared residuals becomes larger. If we have another line which has smaller slope, we have larger error. So we can see that this light blue line minimizes the sum of squared residuals. For general case, if we have p predictors, least square estimator beta hat. Beta hat is, remember that beta naught hat, beta 1 hat. We have p plus 1 term and transpose. This is defined by the minimizer of this SS residual that is defined by summation of epsilon j. We can also write this as epsilon transpose times epsilon, or we can even write this as y minus x beta transpose times y minus x beta, since epsilon is equal to y minus x beta. Remember that y is x beta plus epsilon, so we move x beta to the left-hand side. If you fully write down, that becomes this. And this is actually a quadratic function of . beta 1 to beta, beta naught to beta p. So you can imagine that it's easy to minimize. So you can imagine that suppose, for example, we only have beta naught and beta 1. And we think about the function of SS residual. Then we have surface. So this is the Z is equal to SS residual. This is function of beta naught and beta 1. Then this becomes parabola because this is quadratic form, and you can find a unique minimizer. And actually, the minimizer is given by this formula, beta hat is equal to x prime x inverse times x prime y. So this formula is probably the most important formula in statistics. When I was in Wisconsin, my professor has dyslexia, so she cannot even spell the model. She spell model as M-O-D-L-E, but still always she remembers this formula for beta hat correctly. So that means this formula is really, really important in statistics. And how to prove this formula? Actually, this is surprisingly easy. So let L of beta as SS residual. So that is a function of beta, to be exact, quadratic function of beta. Okay, so now that we want to differentiate this, we can use the product rule in calculus. You can see that the derivative of, okay, so suppose this is F, this is G. This is just transpose, so just I write FG. So this is derivative of F times G plus F times derivative of G. So you can see that if you differentiate the first term, this becomes negative X transpose. We just differentiate with respect to beta. Then we have second term. This is Y minus X beta. So that just comes here, X prime times Y minus X beta hat. Then we have another term, F times derivative of G. Then we have 2. To be exact, we need negative sign here. But anyway, we have to equate to 0. Then you can see that if you expand this, okay, so at first we divide by 2. Then we think about X prime times X beta hat. We move this term to right-hand side, then X prime Y is equal to X prime X beta. So beta is equal to, beta hat is equal to X prime X inverse X prime Y. So this is the answer. So now we finished the basics of estimation, the least square estimator.